And we'll just kind of go through the questions one by one. Hopefully you would have written an answer down. I did post this PowerPoint packet, which just has these 3 slides on it, these 3 sets of checkpoint questions in Brightspace. So hopefully over the weekend, you were able to look at these questions, write an answer down, and then you can now compare that answer to what we're going to discuss here and think about additional questions you may have as well. So the first set of questions here, the first question, define depolarizations and hyperpolarization. And so just to kind of go over the answer here, the depolarizations we said were excitatory events. In other words, they were positive changes of the membrane potential. We can think about them as being upstrokes in the membrane potential because they are moving more positive when compared to that resting value. Hyperpolarizations, on the other hand, are negative changes in the membrane potential. They're moving more negative, and it doesn't have to be more negative than -70 because when the membrane potential is at +30 and it's moving down towards -70, that's also considered hyperpolarization. So it's just any negative change in the membrane potential or an inhibitory change in the membrane potential, okay? So depolarizations, positive changes, excitatory changes, upstrokes. Hyperpolarization are downstrokes, negative changes to the membrane potential or inhibitory events. Question 2, if the permeability of a membrane to sodium increases, would the membrane depolarize or hyperpolarize? And I want someone to answer that because it's kind of really simple. So if the membrane permeability for sodium increases, would the membrane depolarize or hyperpolarize?
Depolarize.
Excellent, thank you. The membrane will depolarize if we increase the permeability to sodium. We know that according to sodium's ECDF, it's going to want to rush right into the cell. It's a positively charged ion. That's going to be positive charge moving into the cell. That's a depolarizing event. Question 3, name the 3 gating mechanisms for ion channels. So again, going right back to the basics here, we know ions cannot go through the membrane. They need a channel to do so. There are different mechanisms to gating those channels. We talked about ligand gated channels where something has to bind to open or close that channel. We talked about voltage gated channels where a specific voltage requirement or condition needed to be met in order for that channel to open up. And there's also a timed component to some of our voltage gated channels. And then we didn't speak as much about mechanically gated channels, but mechanically gated channels are more involved in graded potentials. And so these are where sensory receptors or sensory perceptions are what open up or close those channels. So we more focused on the voltage gated and the ligand gated, but there are those third category of gating of ion channels, which are mechanically gated. Question 4, what is the threshold value of an action potential? And again, I'm going to encourage someone to answer this because it's really straightforward. We talked about this value a lot. So what is the threshold value for an action potential?
-55 millivolts.
Excellent, thank you so much. So that was -55 millivolts. And just to kind of reiterate what the threshold value means, this is the minimum membrane potential value that's required before an action potential can fully occur. And so when we get to -55, an action potential happens. If we don't meet that value, no action potential happens. All right, the second set of questions here, question 1, during the depolarization phase of an action potential, is the membrane more permeable to sodium or to potassium? What about during the repolarization phase? So what are our thoughts here? During the depolarization, which is essentially that upstroke, that rapid upstroke, is the membrane more permeable to sodium or to potassium?
Sodium in the depolarization and potassium in the repolarization?
Yes, that is absolutely correct. Thank you. So sodium is going to be more permeable, or the membrane is going to be more permeable rather to sodium on that upstroke, that depolarizing phase, and it's going to be more permeable to potassium on the downstroke during that repolarization phase. And remember, just bring it all the way back again to the basics here. When we talk about permeability, we're really talking about how many of those channels are open or closed, right? And so more sodium channels are open in the upstroke, more potassium channels are open in the downstroke. Question 2, compare the gating mechanisms of voltage gated sodium and potassium channels. And then why is the timing of events so critical to the development of an action potential? So when you look at the gating of voltage and sodium channels, we know that sodium channels are a little bit more complex. They've got the activation gate and the kind of backup set of gates, which is the inactivation gates. And so we talk about the 3 states of voltage gated sodium channels because of the complexity of having those 2 gating mechanisms. Potassium channels are a little bit more straightforward. Well, let's go back to sodium channels. So they're voltage dependent, and they also have a time dependent component as far as the inactivation gate only. So the activation gate is voltage dependent only. The inactivation gate is voltage and time dependent. As far as the potassium channels, there's only one opening, right? There's no separate gates on the potassium channels. They are voltage and time sensitive. So kind of similar to the inactivation gate there. And then the second part of the question, why is timing of events so critical to the development of an action potential? And we kind of touched on this on Friday. The timing is really important so that an action potential can be a fixed, identical event. It can start and stop in the exact same time. All action potentials can look the exact same. It's also important to have this coordinated timing of events between what's happening on sodium channels, that they're closing at the exact same time that potassium channels are opening up. And so having that timed component is critical to coordinating these events to the exact second, if you will, or millisecond, if you will. And so if the events weren't timed, then this would not happen with the amount of specificity and the reproducibility that it does, where an action potential is the exact same, no matter where we look or how the stimuli changes. Right? If you have a super threshold stimuli versus a threshold stimuli, that action potential looks the exact same. Question 3, during which phase of an action potential are sodium channels closed but capable of opening? So let's start with that first condition. What phase is responsible for sodium channels being closed but capable of opening? And what does that mean as far as the 2 gates?
I could totally be wrong, but isn't it like at rest they're closed but capable of opening? And is that when like the inactivation gate is open?
So kind of partially correct there. So yes, it happens at rest, but the inactivation gates, excuse me, yeah, you're correct. So the inactivation gates are also open. That's what makes it capable of opening. So that's absolutely correct. This is the state of the channel during rest. We're -70 here. And so the sodium channel has those 2 gates. The activation gate is closed. So that's what makes the channel closed, but it's capable of opening because the inactivation gate is open. And so if we get a strong enough stimuli that gets to threshold, the entire channel will open up via the opening up of the activation gates. So that is correct. What about that second condition? During which phase are they open? Excellent. So they are open during depolarization. So after we get to our threshold value, the channels will then open up. And here they're open because both gates are open. Okay, this is what's responsible for the rapid upstroke. What about during which phase are they closed and incapable of opening? So closed and incapable of opening. Excellent. So I'm seeing a lot of response in the chat saying during repolarization, which is true, right? So we have that inactivation gate now closed, activation gate still open. And so the channel is closed essentially, but it's incapable of opening because the inactivation gate is closed, excuse me. Okay. Excellent. So let's look at the third set of questions here. This has to do a little bit with the refractory period. So can an action potential be generated during the absolute refractory period? Can we generate an action potential during the absolute refractory period? Okay, no, yes, that's correct. We cannot generate an action potential during the absolute refractory period. And the reason is we cannot overcome the inactivation gates on those sodium channels, right? That's the main reason behind the absolute refractory period. That's corresponding to depolarization, right? Just intuitively, you can't have another action potential during the upstroke of an existing action potential. But then more importantly, during the repolarization phase, we cannot have another action potential because the inactivation gates are closed. In other words, the sodium channels are inactivated, okay? So that's the mechanism there behind the absolute refractory period. What about the relative refractory period? What's happening there? So can we have an action potential during, excellent, thank you. So if we have a strong enough stimuli, yes, we absolutely can. We can overcome the overshooting of the membrane potential. Remember, the membrane potential gets slightly more negative during that relative refractory period. And so it's getting closer to potassium's equilibrium potential. It gets all the way down to about -85 or so. And so we need an even stronger stimulus to depolarize us to threshold from -85 than we would need to depolarize us from -70. So if we had a strong enough stimuli, we absolutely could generate a second action potential during the relative refractory period. Question 2 here, during the absolute refractory period, are the majority of sodium channels open? Are they closed but capable of opening, or are they closed and incapable of opening? So what do the majority of sodium channels look like during the absolute refractory period? Okay, so I'm seeing two different responses here in the chat. We've got closed and incapable of opening, and then someone else has closed and capable of opening. So remember, we're corresponding the absolute refractory period to repolarization itself. So what's the state of the channel like in repolarization, right? Those sodium channels are closed, but they're incapable of opening, right? Remember, the inactivation gates are still closed. So during absolute refractory period, the channels are in their state of repolarization, or the action potential is in the phase of repolarization. And so the channels are closed, but they are incapable of opening because the inactivation gates are closed. Remember, that will not get back to the normal state of the channel. The inactivation gates will not reopen until we get back to the resting value of -70. Ready?